Good day everybody. This is a very important integral minus infinity to infinity sin x over x dx, and it becomes imperative that we learn how to integrate this. Now what I will do is I will be approaching this question in different ways of integration. The first and foremost technique that I would be utilizing would be Laplace, using Laplace transforms, and then subsequently in the next lesson I will be utilizing a different technique, and so on and so forth. So first let me start off by using Laplace transform to integrate this. Now there is a very important integration property which we have studied. Say for example, if we were to be given integral negative a to a, say f of x times dx, then I can rewrite this as integral, or I should say 2 times integral 0 to a f of x times dx, provided f of x is an even function. So that is the requirement. And in this case, just consider sine of x. Let me just take f of x to be equal to sine of x divided by x. Now let me take x to be equal to negative x. So that is a check. So that would mean f of negative x is equal to sine of negative x divided by negative x. And since sine x is an odd function, this is going to be negative sine of x divided by negative x. So negative will become positive, giving me sine x over x, which is subsequently nothing but f of x. Now since f of negative x gives us f of x, this implies the given function f of x is even function. So I did all these things just to show you that the function that we've been given is even. So since it is even, I can rewrite the integral as 2 times integral 0 to infinity sin x over x times dx. Now let me define a new function. Let us define a new function. So let me just take f of some t is equal to integral 0 to infinity sine of dx is a parameter, divided by x dx. Now you will be wondering, why did I define this? Now if I'm not able to define this, then it is not possible for me to apply the Laplace transform and extract the solution. So I need a function. So that's the reason I'm defining a function. Now this function will represent the given function, our original function, when t is equal to 1 or 0. When t is equal to 1, this is going to be equal to 0 to infinity sine of x divided by x times dx. So if I am able to get this value, I can substitute that over here, and subsequently the solution is obtained. Now this is just a deduction, so I have got no use for this as of now. So let us start by utilizing f of t. F of t is this. Now what I wish to do is I would like to take Laplace transforms. Now when I take Laplace transform for the function, this would mean I get L of f of t. Now L of f of t, what is the Laplace transform of a function? It is given to be as 0 to infinity the function f of t times e raised to the power of negative st times dt. I have done a lot of videos on Laplace transforms. A complete lesson is available on Laplace transforms and inverse Laplace transforms. I suggest that you can go up and look onto that and extend your domain knowledge. So having mentioned that, let me move on. So this is the definition. I'm taking f of t to be this, and then I'm taking Laplace transform of the function, and Laplace transform of the function is defined to be in this fashion. But f of t is this, so take this and substitute it here. So this is equal to integral 0 to infinity, in place of f of t, substitute this, is going to be 0 to infinity sine tx divided by x, and you got e raised to the power of negative st, and you can place that dt and then dx. Now you got two variables, you got a t here, you got a dx here, or I should say x here and a t. So what I wish to do is I would like to push or move this x component out. So 0 to infinity, let me place 1 over x here, and 0 to infinity. So this is going to be just sine t with x, something of this fashion, and then e raised to the power of negative st with dt there. So I'm blocking this and I place dx outside. Now if you would have come across the definition of Laplace transform, suppose you have something like this, 0 to infinity, and you have sine at e raised to the power of negative st dt. Now what is this? This is actually a Laplace transform of sine at. So Laplace transform of sine at is defined in this fashion. So I'm just specifying it that. So I have actually received, or I should say I have formed a Laplace transform from the function, and all I need to do is to apply the result for the Laplace transform of sine at. Now in this case we do not have at here, but we got tx here. So t is the variable and x is the constant. So we know that Laplace transform of sine at is nothing but a over a squared positive a squared. This is the formula. So if we were to apply that over there, this is going to be integral 0 to infinity 1 over x. So in place of a, I've got x, place that, divided by a squared positive x squared times dx. So clearly this x and x can be cancelled, and this is off. And the reason I'm saying off is because this has produced us this result. So all we got now is to integrate 0 to infinity dx divided by a squared positive x squared. So now x is the variable and this is actually a constant. So what I'm going to do is I am going to be taking a squared out. So if you were to take a squared out, so let me write this as a squared of 1 positive x over s whole squared with limits 0 to infinity. So this can be pushed out. So let me use the space here. So this is equal to 1 over a square, limits are 0 to infinity. So I got dx over x over s raised to the power of 2 positive 1. Now what I wish to do is I would like to make a substitution. Let x over s be equal to some p. So dx over s is equal to dp. So dx is equal to s times dp. The limits won't change. The limits will still be 0 to infinity, because if you had to substitute upper limit, p will be infinity. If you had to substitute lower limit, p will be 0. So no harm is done or no change for the limits. So it's going to be 1 over s squared, and in place of dx I'm going to be substituting s times dp. In place of x over s I'm going to substitute p. This has got 2 there, so p squared positive 1. So clearly 0 to infinity is the limit, so place that out, and s and s gets cancelled, giving you 1 over s. Limits are 0 to infinity. dp divided by p squared positive 1. Now this is nothing but tan inverse of p, right? It's similarly of the form dx over x squared plus 1, right? So that's tan inverse of x. So similarly in this case this is going to be tan inverse of p, and the limits are 0 to infinity. Now if I substitute the upper limit, I'm going to get 1 over s tan inverse of infinity negative tan inverse of 0. Now tan inverse of 0 vanishes. Tan inverse of infinity will give me pi over 2. So you get 1 over s times pi over 2. Now on the left, what do you got on the left? If you were to see, we took Laplace transform for f of t. So let me use this side of the page. So therefore L of f of t is equal to 1 over s times pi over 2. But we need f of t. Why do I say we need f of t? Because if you can clearly see, we defined f of t to be like this. And subsequently, if I were to obtain a value for the integral, then I need to know what is f of t. Otherwise, it wouldn't be possible for us to get the result for this. Right? So, to get f of t, push L to the other side. So that would mean it will become L inverse of 1 over s times pi over 2. Now Laplace inverse is a linear operator. So that would mean you can take the constant out. So if you were to take the constant pi over 2 out, you get L inverse of 1 over s. But what is L inverse of 1 over s? That's nothing but 1. So that is equal to pi over 2. So subsequently you have got f of t to be equal to pi over 2. So let me just write that down here. So therefore f of t is equal to pi over 2. Now what does that mean? Clearly, no matter what the value of t is, outcome is going to be pi over 2. There is no t involved here at all. So this is going to be a constant. So take this f of t is equal to pi over 2, and subsequently, irrespective of value of t, say for example, over here, no matter what the value of t is, still the function is going to give me pi over 2. So all I need to do is take that value which I've got. So this is going to be producing me pi over 2, even though t is equal to 1 or any value. Now remember, this is equal to pi over 2 for all values of t greater than 0. So that is an important condition that you will have to know. The t is strictly greater than 0. So having mentioned this, take the value and substitute it here. So this is equal to 2 times of, I am substituting this pi over 2. So as I mentioned to you, the outcome has got no whatsoever impact with regard to the value of t. But the only requirement is t is strictly greater than 0, because we are just getting a constant pi over 2. So 2 can be cancelled, giving me pi. So the outcome is pi units. That's the solution for this beautiful integral minus infinity to infinity sin x over x times dx, which has been done using Laplace transforms. Thank you everybody. Enjoy your night.